If you look at the famous King's Chamber, its walls and its roof are the ceiling of the King's Chamber are all made with gigantic granite blocks.
Grok AI finally revealed how Egyptians may have cut granite, but the answer opened a stranger problem. The known tools explain a lot, until the evidence gets too precise. Deep in the marks left on ancient stone, one detail seems to resist the simple explanation. It is small enough to miss, but serious enough to question the whole process. And when Grok compared the proof, the mystery became sharper. How could the cut make sense, when the evidence itself does not? The problem Grok was given. Grok AI, built by XAI, was given a very specific problem. How did ancient Egyptians cut and finish granite with the tools we know they had? This was not a vague question about pyramids or lost technology. The data included archaeology, engineering, tool experiments, and measurements from Giza, Aswan, and more than 140 years of debate. Grok's job was simple: separate what the evidence confirms from what still does not fully fit. Aswan syenite sits at the center of this mystery. This hard granite-like stone measures around Mos 6 to 7, and it was quarried about 900 kilometers from Giza. The Egyptians used it in places where mistakes were not easy to hide: the King's Chamber, stone sarcophagi, ceiling beams, and obelisks weighing hundreds of tons. So the real problem is not whether they worked granite. They clearly did. The question is how precise they could make it. Dolerite pounders, copper saws, copper tube drills, and loose quartz sand are the confirmed tools. These are not guesses. They have been found at quarry and construction sites, and their marks match many ancient surfaces. Dolerite around Mos 7 could pound and break stone. Copper with sand could cut by abrasion. But the difficult part is efficiency and precision. Could these tools explain every fine groove and finished granite surface? Grok's analysis sorted the evidence into 3 categories. Bulk quarrying was well explained by confirmed tools. Rough cutting was mostly explained by copper, sand, labor, and time. Precision finishing was different. In that 3rd category, the evidence stopped fitting cleanly. The large stones were not the main problem. The problem appeared in small marks, tight surfaces, and drill features that looked more controlled than expected. Flinders Petrie had already seen this problem in 1883, long before AI, XAI, or modern online debate existed. While studying granite drill cores at Giza, he measured spiral grooves and calculated cutting results that he described as beyond our power of explanation. That matters because this gap was not invented by Grok. Grok only pointed back to a documented problem that has been sitting in the record for 140 years. Grok did not struggle with the giant stones or the rough quarry marks. It struggled with something much smaller, a narrow groove in a granite core that should not look the way it does. The unfinished obelisk, where the evidence starts. Aswan gives this investigation its first solid piece of evidence. The unfinished obelisk still lies in the ancient quarry, about 42 meters long and estimated at nearly 1,200 tons. It was never fully removed from the granite bedrock, which is why it matters so much. Unlike a finished monument at Giza, this one is frozen in the middle of the work, showing the quarrying process before the stone ever left the ground. Cutting channels around the obelisk show the marks of dolerite pounders, not saw blades or hidden machines. Across the Aswan granite, there are thousands of small, rounded impact marks, the kind made when hard stone balls are driven again and again into one place. The process was slow, physical, and rough. Each strike removed a little more stone, not by slicing cleanly, but by crushing, bruising, and gradually weakening the rock. Dolerite pounders have been found across the Aswan quarry in large numbers, with many weighing around 5 to 12 kilograms. These stone balls match the marks in the channels, which makes this part of the ancient method hard to dismiss. The evidence is not only written in tools, it is written directly into the granite surface. For bulk removal, the Egyptians had a working method, and the unfinished obelisk shows it clearly. A crack in the obelisk ended the work before it could become a monument. That failure preserved the scene at the exact point where the quarrying process stopped. Modern researchers can still study the channel width, depth, tool marks, and the way the granite was being separated from the bedrock. In a strange way, the broken stone became more valuable as evidence than a completed obelisk would have been. Finished granite at Giza creates the harder question. The unfinished obelisk explains rough cutting, but it does not show the final finishing stage seen in the king's chamber, sarcophagi, or smooth internal granite surfaces. The quarry marks are impact marks, not precision marks, so the evidence starts clearly at Aswan. But it does not follow all the way to the tight tolerances found hundreds of kilometers away. The bulk cutting method is visible and well documented at Aswan. But once the granite became precision work, the marks changed, and the next clue came from Petrie's drill cores. Petrie's drill cores Flinders. Petrie arrived at Giza in 1880 with a very different goal from the one people might expect. He was not there to chase a mystery about lost tools or ancient machines. He came with instruments, measurements, and a personal mission to test his father's idea that the Great Pyramid held hidden mathematical meaning. Within months, his own data broke that theory, and his attention moved to something more physical, the stone itself. Petrie began documenting the granite at Giza, and that is where he found the evidence that still matters today. Among the objects he studied were tubular drill cores, small cylinders of granite left behind by ancient hollow drills. These were not giant blocks or finished walls. They were narrow pieces of stone with spiral grooves around them, and Petrie measured those grooves with the same care he used on the pyramid. Those spiral marks gave Petrie a problem he could not easily explain. By measuring the groove spacing and depth, he calculated a feed rate, meaning how far the drills seemed to move forward with each turn. That number mattered because it suggested the pressure needed to cut through granite. Petrie believed that kind of pressure would have destroyed a copper tube before the drilling was finished. In 1883, Petrie published the results in the Pyramids and Temples of Gizeh, and he did not pretend the answer was simple. He described the cutting power suggested by the cores as something he could not account for at the time. That sentence is why this evidence still matters. The mystery was not created by modern internet debate or Grok AI. It was already sitting in Petrie's own measurements more than 140 years ago. Petrie's numbers were strange enough, but one detail inside those grooves made the problem even harder: the way the cut passed through the crystals themselves. The crystal sectioning detail, where the evidence stops making sense. Granite looks solid from a distance, but under the surface it is a mix of different crystals. Quartz can reach Mohs 7, feldspar sits around Mohs 6, and mica behaves differently again. That matters because a loose abrasive tool does not cut granite like a modern blade. It scratches, grinds, and breaks the surface. When it meets crystal boundaries, the cut usually deflects or fractures instead of passing through cleanly. Petrie noticed something strange in the Giza drill cores. Some spiral grooves appeared to pass through individual quartz and feldspar crystals instead of breaking around their edges. That detail is small, but it is serious. A groove only a few millimeters wide can reveal the behavior of the tool that made it. In this case, the marks seemed too steady for the standard copper and sand explanation to answer easily. Sand abrasive drilling works by using loose, hard particles between a copper tube and the granite. The sand does the cutting, not the copper itself. This method can work, and later experiments showed it can drill stone. But it creates a rougher, more scattered cutting action. It does not usually hold one clean direction through separate crystals with different hardness levels, especially through quartz at Mohs 7. This is why the crystal sectioning detail has lasted for more than 140 years as a real problem. Since Petrie documented the cores in 1883, researchers have explained quarrying, transport, rough cutting, and many tool marks. But this specific pattern, a groove cutting through crystals rather than breaking around them, has not been clearly reproduced under confirmed ancient Egyptian tool conditions. The issue is not that Egyptians could not cut granite. The issue is that this mark does not match the tested signature. Mainstream Egyptology can explain the quarrying, the transport, and much of the rough cutting. But since 1883, no experiment has cleanly matched this one groove signature. What the experiments tested. Dennis Stocks, a British experimental archaeologist, became one of the most important names in this investigation because he actually tested the tools. In 2003, he published Experiments in Egyptian Archaeology, where he worked with real granite, copper tools, and sand abrasive. His work matters because it moved the question away from guesswork. Instead of asking only what ancient Egyptians might have done at Aswan or Giza, Stokes tried to repeat the process by hand. Stokes confirmed something important. Copper saws, copper tubes, and loose quartz sand can cut Aswan granite. The copper is not harder than the stone, but the sand does the real work by grinding between the tool and the surface. This means the basic method is real, testable, and does not require lost machines. For rough cutting, the standard explanation has strong support from 2003, Aswan, copper, and sand. Cutting rates created the harder problem. Stokes measured granite drilling in millimeters per hour using hand pressure and confirmed ancient-style tools. Those numbers showed the method works, but also made the scale difficult. When the same slow rate is stretched across the amount of precision granite at Giza, the labor question becomes heavy. The tools can cut, but the time needed for the finest work is where the explanation starts to strain. Petrie's drill cores made that strain more specific. Stokes's experimental cores showed the kind of crystal boundary deflection expected from abrasive cutting. In simple terms, the cut tends to break or shift when it meets harder crystal edges inside granite. But Petrie's 1883 cores from Giza showed a different pattern. The ancient marks did not match the experimental marks cleanly, and that difference is the real issue. The tools could cut granite, but when Grok compared the experiments to Petrie's cores, the marks did not fully line up. What Grok found when it processed the full evidence. Grok's full analysis separated the granite evidence into 3 clear stages. The first was bulk quarrying at Aswan, where dolerite pounding explains the rough removal of stone. The second was rough cutting and transport, where copper tools, quartz sand, labor, and the Nile make the process understandable. But the third stage, precision finishing, did not line up as cleanly. That is where the investigation became harder. Precision finishing brought the strongest contradiction into view. Grok focused on Petrie's 1883 drill core measurements, especially the feed rate and crystal sectioning, then compared them with measurements from the King's Chamber coffer. Both datasets pointed to work that seemed to sit near or above the demonstrated limits of Dennis Stokes's 2003 experiments. The problem was not one loose claim. It was a pattern across multiple pieces of evidence. Grok did not claim to solve the problem, and that is what makes the result more serious. It simply marked the gap. Confirmed tools explain most ancient Egyptian granite work, especially quarrying, cutting, and shaping. But one physical signature in the precision evidence does not match what copper tubes, loose quartz sand, and hand pressure have produced in tested conditions. The unanswered part is small, but it is measurable. This finding is not about magic, aliens, or a hidden machine being proven. It is an engineering problem. The confirmed ancient toolkit has a tested performance ceiling, and some precision evidence at Giza appears to sit beyond that ceiling at specific points. The distance between those two things is the real mystery. Grok did not make the gap bigger. It made the gap clearer. Grok identified the gap, but identifying a gap is not the same as closing it. The next question is what kind of precision finished objects at Giza made that gap impossible to ignore? The precision finishing problem. King's Chamber turns the granite question from rough cutting into precision work. Flinders Petrie measured the granite coffer inside the Great Pyramid at Giza and found internal flat surfaces accurate to about 0.01 inches, or roughly 0.25 millimeters, across several feet. That number matters because it is not about moving stone. It is about finishing stone so evenly that Petrie compared it to serious Victorian-era manufacturing, not ordinary hand shaping. 9 granite beams above the King's Chamber make the problem even heavier. Each beam weighed around 25 to 40 tons, and the stone came from Aswan, roughly 900 kilometers away. These were not small workshop pieces. They were massive blocks transported by river, lifted into place, and fitted with joints so tight that Petrie recorded no visible gaps with his instruments. The strange part is not only the size, it is the fit. Christopher Dunn and other modern observers focused on another detail: surface finish. Some granite boxes in the Valley of the Kings show flatness across large surfaces that looks more like controlled finishing than random stone removal. In modern work, that kind of result often comes from grinding or lapping, where pressure is applied evenly over a wide area. Abrasive drilling and pounding do not naturally create that same controlled surface. Granite sarcophagi add one more piece to the same pattern. In several cases, the lid-to-box contact is described as tight enough that a thin feeler gauge cannot enter along parts of the edge. That means the top and bottom surfaces had to match across heavy stone pieces weighing multiple tons. A rough tool can shape a block, but matching two large surfaces to that level is a different problem. Section. End transition. The rough methods are visible. The finished objects are still standing. But the missing step is the one that turned broken granite into precision stone. The three explanations. What fills the gap? Mainstream Egyptology gives the first explanation, and it is not weak. Ancient Egyptian workers had confirmed tools, real skill, and long working periods at places like Aswan and Giza. Copper, quartz sand, dolerite, and human labor can explain a large part of the granite work. The problem is not whether these tools worked. The problem is whether they can explain the exact 1883 drill grooves, the 0.01-inch tolerances, and the finest finishing marks. A second explanation is more practical, and it does not need advanced machines. A weighted drill frame, a loaded crossbeam, or a bow drill system could have pushed a copper tube downward with steady pressure. This would help explain why Petrie's feed rate calculations seemed so difficult. Wood, rope, leather, and stone weights were all possible materials in ancient Egypt, but no full-scale test has clearly proved this setup on Aswan granite. A third explanation moves into more speculative ground. Some writers, including Christopher Dunn, have suggested sonic cutting, ultrasonic tools, or older advanced machinery. These ideas may seem to answer the precision problem at Giza, especially around the King's Chamber and granite boxes, but they lack physical equipment, archaeological proof, and experimental support. Grok treated these as unsupported theories, not confirmed answers. Grok's key point was careful. The mainstream explanation cannot simply be thrown away, but it also has not fully reproduced the specific groove signature found in Petrie's cores. The same issue applies to some precision measurements from Giza, including flatness and surface finish. After 140 years, the gap is still not about all granite cutting. It is about a few measurable features that have not matched any tested method. The most realistic answer may not be a lost machine. It may be one missing wooden and rope device that disappeared long before anyone knew it mattered. The most realistic version, ancient Egyptian granite work, most likely happened in 3 stages, and the first 2 are easier to understand. At Aswan, workers used dolerite pounding to remove large sections of stone. After that, rough cutting and transport relied on copper tools, quartz sand abrasive, labor, and river movement toward Giza. Those parts fit the evidence well. The harder part begins when rough granite becomes precise granite. Petrie's problem may be explained, at least partly, by a missing mechanical setup. A weighted drill frame, loaded boom arm, or rack system could have pushed a copper tube into granite with steady pressure. That would help explain the force behind the 1883 feed rate calculations without needing unknown metal or impossible tools. If such a device used wood, leather, and rope, it could disappear from the record without leaving much behind. Crystal sectioning remains the stubborn detail. Even if a loaded copper tube with quartz sand explains stronger pressure, it still has to explain the clean path through quartz crystals. Quartz sits around Mohs 7, and abrasive drilling normally breaks or deflects at crystal boundaries. Dennis Stocks tested copper and sand in 2003, but the specific Petrie pattern from Giza has not been clearly reproduced. Grok's result was careful, not extreme. It did not say ancient Egyptians needed lost technology, and it did not reject the confirmed tools from Aswan, Giza, or the 1883 drill core record. It reached a grounded middle point. Most granite work makes sense with known tools, especially if those tools were used in a setup not yet fully tested. One physical mark still does not fit neatly. The larger process may be mostly understood, but one narrow groove still refuses to match the tools we can prove existed. The groove that Grok could not explain. Petrie's drill groove remains the smallest detail with the biggest weight. In the Petrie Museum at University College London, the surviving granite cores still carry the marks he documented after 1883. The key detail is a groove passing cleanly through a quartz crystal instead of breaking around the boundary. That matters because it is not a legend or a guess. It is a physical mark on a real artifact. Abrasive cutting should leave a different kind of signature. A copper tube, loose quartz sand, and hand pressure cut by random microfracturing, not by slicing like a modern machine. When that process meets crystal edges inside granite, especially Hardmo's 7 quartz, the path usually becomes rough, ragged, or deflected. Petrie's core showed something cleaner, and that is why this one groove keeps returning to the center of the mystery. Experimental work has reproduced many parts of ancient Egyptian stone cutting, but not this exact mark. For more than 140 years, researchers have tested copper, sand, granite, pressure, and drilling methods. They have shown that ancient-style tools can cut stone. They have shown that the basic method works. But no published experiment has clearly produced a drill core where the groove sections are quartz crystal the same way Petrie described. Grok's role was not to invent a new theory. It compared the full evidence base. Aswan quarry marks, Giza drill cores, Dennis Stock's 2003 experiments, and precision measurements from finished granite objects. The result was careful, but important. Most of the granite work fits known tools. One feature, at the most precise level, still sits outside what has been demonstrated with confirmed ancient Egyptian materials. No wild claim is needed here. One narrow groove is enough to keep the question open. If this granite mystery made you question what ancient tools could really do, subscribe for more grounded investigations and tell us what you think Grok missed.